Okay, so what is the first thing you do when you start the project? For me, it's turning off my autopilot. Because I realized I like to use CQRS, and not two projects are the same. So if projects are not the same, so why should we be applying all the structure, all the technologies, all the patterns in the same way on various projects? So on every single project, I try to turn off my autopilot to think from the beginning and to debate with myself to be able to defend the choices I make. And it is the same if I go with teams. When I'm leading a team, I don't want to be a HIPAA decision. Do you know what HIPAA is? Highest paid person opinion. So I try to make the decisions, tell them to my team, try to defend them, and try to listen to arguments. So today, I'm actually going to talk about CQRS, how to do it, but with some thinking. Also, I'll try to explain to you why developers actually love changes, why you should read ancient books, how to recognize a SIT, or are you maybe one, and actually how many databases you need on a project. So first question is, what is our job? What we are actually doing as developers? We're not building systems, we're changing them. If you look at the gist of what you're doing, you will first build a system, then you deploy it into production, and then you will spend years changing it. So when you look percentually, what we are doing is actually we are changing the systems. And we usually don't love it. We despise it. It's a disturbance factor for us. So why are changes so hard and what we can do to make them easier? And I will reach into 1999, and I'm going into ancient history when it comes to the timeline of our industry. And I will reach to a technique called Øredev framework, which was developed for managers. And I'm going to try to apply it here. According to this framework that was made for managers to empower them to more easily reason about the systems, all systems can be divided in these 5 categories, starting with obvious systems or simple ones. This would be very, very small projects now that we apply this to our profession. These would be very, very small, very simple one-day projects. Obviously, we don't need any techniques. We build it, we use it, it's a throw-off project. Then you have complicated, complex ones. You have chaotic ones. I don't want even to speak about them. I hope I never encounter one. And if we cannot categorize any of them, then we use, okay, this is disordered projects. So what's interesting here are complicated and complex projects. And you remember the Facebook, it's complicated, or maybe it's complex. But when you look at complicated systems, this is actually what we are building on a daily basis. This would be system or domain, to be more precise, which is opposite of easy. You don't have straightforward relationships between the cause and the effect. You have complex rules, so you usually need domain expert, or you need to become one in order to build such a system. You have very high number of information variables that are affecting the system. And essentially, this is where we try to apply design practices, good practices and design patterns in order to conquer this domain. And this is basically every single non-trivial project that you're building. However, over time, as you start to change your system, you run into the domain of complex systems. So essentially, you start from one implementation, you release it into production, and then as you start to change it, it's becoming complex. And complex is opposite of simple. You're entering the realm of unmanageability. You cannot make accurate predictions anymore. You have large amount of factors which are affecting your system. And this is actually domain of emergence. So when you think about it, what we are doing, we are building complicated systems, and then we are pushing those systems towards complex ones. And this is because of complexity. Now, Fred Brooks in 1986 divided complexity into two domains, essential one and accidental one. Essential one is the complexity of the domain you're implementing. So this would be understanding domain you're building, discovering the rules, talking to experts, talking to people who will be using your application. And then on top of that, we build accidental complexity. So whenever you make a choice to enter marriage with framework, with design pattern, with CQRS, this is accidental complexity. So we cannot change or we cannot avoid essential complexity, but what we can do, we can minimize accidental complexity. And one of the most complex or complicated, however what you want to take, its domains is mathematics. And in mathematics, we can reason clearly. We have over millennia of reasoning in mathematics. So when you think about mathematical functions, and when you look at something this simple, start reasoning about it, I have a square root function where I call it with numbers like 25 or 9, I will get back results. If I have a variable, a and b, if I pass them to a function, what will happen? I will get back square root, but the value of a, b will not change. And of course, it would be ridiculous now that we know mathematics that a and b would be affected by taking square root. Then, does order of calling functions square root of a and b matter? It does not matter. So if I have f of a and then I'm calling f of b, the result will be the same if I turn them around. If I call square root of a, will it change b? Or will square root of b change a? No. So we have predictability. Things are behaving the way we are expecting. And you could formulate these intuitive rules of mathematics into side effects, into determinism. So when you call mathematical function, you don't have any side effects. Why they are called side effects? So they are additional effects. So taking a square root is the primary function, primary functionality. I won't get any bonus functionality, and usually I don't want to have it. Otherwise, I'm in problem. Mathematical functions are deterministic, and this means if I call it 25 times, 50 times, 500 times with certain arguments, every single time I will get the same value. So determinism is same as predictability. And such functions are called pure functions. No side effects and determinism. And as a result of this, you have something called referential transparency. So everywhere where I have square root of 25, I can go and replace square root of 25 with the result of evaluation, which would be 5. And nothing will change. And we know we have hundreds of years of empirical evidence that these properties are good. On the other hand, when you look at the same concept of functions in programming, you can have side effects. Now, not all side effects are bad. They are making our application actually useful. So, printing on a printer, sending email, writing to a database, interaction with the environment. Functions in programming can be non-deterministic. So you can call it a couple of times with same arguments and get different results. And of course, this is what makes them unpredictable. And this is impurity. So the lack of non-determinism and the existence of side effects is what making our functions not pure. Therefore, we are lacking referential transparency. And when you think about referential transparency in programming, it's actually inlining. This is what we are attempting to do to optimize. So overall, functions in programming languages or methods or subroutines, as whatever you want to call them, they are interacting with the environment. Function or method which is not interacting with the environment is called isolated. And usually when you write tests, unit tests, you want to have isolated methods. So methods which are not isolated can read and write to and from environment. And lack of all these good properties, predictable properties of functions, are materializing into side effects which can be bad. So most of the times, unfortunately, side effects are not good, they are not intended. And then, as a result of that, we have no predictability, when we cannot reason clearly, it's hard to test. It's hard to reuse functions because they are interacting with environment. So I cannot just copy and paste function. I cannot take mathematical lemma. I can take mathematical lemma and copy it to another paper. It will work. But here we have problems with reusability. Since our functions are interacting with environment, try implementing concurrent solution. You will run into problem. So we are starting to use immutable data structures so that two pieces of code are not messing with each other, or when you pass argument to function, to protect argument from being changed by a function. And try remembering all the times you had problems with debugging, with refactoring. Also dishonesty. Honest method will tell you by the signature what it's doing. Remember Java, okay, this method will throw exception, or this method is accepting certain number of parameters and returning value, and that's it. Such methods are called honest methods. So if you have method with side effects, this is dishonest method because it's doing something else besides what it's claiming to be doing. And then you also have problems with cognitive load. So this means you open a project you see for the first time in your life and you have a hard time comprehending it simply because of lots of side effects. Also, idempotency is a good property of systems, especially if you're building distributed system, because there's almost no such thing as exact once delivery. When you try to think about interaction of the components of the distributed system. So if you have idempotent system, this means that if you call distributed system once or twice or 5 times, final outcome will be the same. You will not create 5 emails to be sent, you will create just 1. So this is what typical stereotypical architecture would like in your application. And this is what we usually start with when we learn programming, when we exit university, when we have young colleagues, juniors on the project. This is what everyone is familiar with. You have a client, you have communication with the client on the server side, application services, DTOs, view models are going back and forth. This is something we all started with. And you can already assume that this is not going to work so well in big projects. Why? Because over time, people were programming, people were developing, they were making conclusions. And again, going to ancient history in 1988 and second edition of this book, 1997, Bert and Meyer, who came up with Eiffel programming language, wrote this 1370 pages book, very heavy. You can use it for bodybuilding, or you can open it and learn some great things. Great book indeed. And this was the first book where I managed to find mentioning of software craftsmanship. And what is also interesting, this is the first book I managed to find a comparison of a class design being equal to interface design. So when we are designing classes, we are actually designing some kind of a contract or interface, and we are giving promises that if you use this interface in an honest way, we will be honest as well. We will do what we are promising to do. So in chapter 23, Principles of Class Design, Bertemeyer comes up with something called CQS. CQS is Command Query Separation Principle. And it states that all interactions between the client and the system should be divided into 2 categories. They should be separated into commands and queries. Commands will change the state of the system. They will produce some effect on the system, but they will not return you any results. While queries will return you the state of the system, but they will not affect the system. And this was observed on many, many projects, and this is something he concluded, he formulated as a principle. So if you start writing your applications like this, what will happen? Commands will produce side effects, but queries will not. So you see, you're halving the surface of the functions or the interface of your application that can make side effects. And then again, not all side effects are bad. It's a simple principle. Asking a question should not change an answer, because answer is being calculated from the state of the system. And this is applied to the surface of your application, not below the surface. And of course, this is not a dogma, this is not a rule, this is good principle. So usually when you start observing what people are doing, they are implementing CQRS systems, and then you start talking to them. And then there's a dilemma. Can I save something to a database, and can my application return ID that was generated by a database? So you know that only sits these in absolute, or if you want to pop a value from the stack, should you implement two functions, one for peeking top of the stack and the other one for popping it? And of course the answer is no, you should be pragmatic. So CQRS is not your goal. CQRS is a tool, is a principle you're using. So your goal is to make implementation which is manageable, not to follow the dogma of CQRS. So be pragmatic. And then when you apply something like this, your stereotypical architecture will evolve into CQRS architecture, where the surface of your application is divided into commands and queries. So you will send a command to alter the state of your system, and then you query system, you will get back the state. And practice shown that this is a good idea. And I was also first using this, and it turned out for me personally to be working well. And then in around late 2010, Greg Young started promoting something called CQRS. So this is not a separation anymore, because separation is setting things apart on the surface. This is actual inequality, what segregation is. So what Greg did, he evolved the idea of CQRS, and he propagated it to the very, very end of the system through all the layers. So if you think about your application, CQRS is propagating this division into commands and queries through all the layers of your application, all the way down to the database. So he actually segregated the whole system into two subsystems, one for querying and one for sending commands. And of course, Greg was promoting event sourcing. So when you think about it, if you have user interface generating commands, these commands are transformed into events. Events are saved somewhere in some kind of storage. And now you need some kind of mechanism to generate projections to calculate the state out of the events. So normally, being pragmatic, he was using two storages. So one storage for events, one storage for projections, or for computing states of the aggregates, or for computing whatever state you might need. And you can see now CQRS architecture. Starting from the surface, we propagated this division all the way to the database level, and he ended up with two databases. So this is pragmatic approach. I'm using what I need to use to produce effects that I need. So as a consequence of using such architecture, you have scalability because you can scale reads and writes independently. Whenever you have this proportion between the reads and writes, this kind of architecture provides you with easier way to optimize just one or the other side. You have more flexibility, and your complexity is constrained again, because you clearly know which pieces of your code, which functions will change the state of your system. And of course, for some other issues like security, you also have more granular approach. So again, when using something like this, it turned out to be a good thing. So this is how CQRS and event sourcing would look like. You will send a command will be validated, it will be authorized, it will be materialized into one or more events. These events will be stored inside of some kind of event store. Again, specialized store for events, where you have streams, where you have append only. And when I say append only, this also implies ability to implement high performance functions, because you're only appending, you're eliminating resource contention, all these things that are making headache for us. And then, based on the events, you are computing the state. And you have a concept called eventual consistency. And of course, it's natural if you're writing to one database and reading from another, there will be some time delay before projections arrive to read-only database. But it turns out, when you're junior, you're scared of such things. You're thinking sequentially, you're thinking in a way, okay, I changed the state of the system, it needs to be visible immediately. It turns out when you start building applications that 80, maybe over 90% of scenarios, business scenarios, can sustain eventual consistency. In practice, this means 10, 20, 30 milliseconds, maybe 50 milliseconds. But when you think from the perspective of interaction with the system, after writing to a system, usually there will be some navigation to other screen. So in most cases, this is not a thing to be worried about. And then when you start with this, you can apply different architectural patterns. So for example, what we had were projections. We were storing projections inside of a database. Well, we can be pragmatic. Maybe we don't need projections database at all. Maybe it doesn't have to be a database. Maybe we can store it in a memory, or maybe we can store it in some kind of distributed cache like Redis. And again, when you think about it, what would be the first thing you would do when you have application that is slow? Well, you would be putting some kind of caching layer in front of it. So you just reach CQRS without even thinking about CQRS, because you introduced specialized read-only store to amplify your read side. So we are coming down to being pragmatic. Pragmatic in the sense of using proper tool for the problem we have. Whenever you use some solution, you should have clear answer what problem you're solving. It must not be a cargo cult, just because a book said you should use CQRS or event sourcing. This should be actual solution to actual problem you have. So if you're pragmatic, you may end up with 3 databases. You will have your domain objects being manipulated by application service. You will store it in maybe relation database. But then on the read side, you have a product catalog you need to search with a full text search. You need to maintain shopping cart. So, okay, you will use Elasticsearch for full text search. You will use, let's say, relational database or document database for maintaining shopping cart. So you can have 3 databases. Or if you're using something like RavenDB, for example, you can use single database and still end up with 2 databases, because RavenDB is composed of key value store and of indexing engine inside of a single database. So when you're writing to this database, you will be writing to key value store. Any change in key value store will trigger indexes to be recomputed. And when you have queries arriving at the database, these queries will be served from indexes. Indexes are kind of combination of materialized views and cache. This is all about being pragmatic. Using proper tools. It's not about using 2 separate databases. This is one sentence. You need to think about what you're trying to achieve. So sometimes you will not even go to propagate CQRS all the way through. You will propagate it to the extent that you need. Because this is not a dogma. This is us being pragmatical developers. And of course, CQRS can be used in various scenarios. If you're not familiar with actor model, is anyone using here actor model? Great. So I think this is future computing. So Go look at the actor model, totally, completely different computation model. CQRS is working well with it. If you think about eventual consistency will guide you to the pit of success when building high-performance systems, because one of the worst things you can do in distributed systems and high-performance systems is creating synchronous calls. So the moment you separate these two databases at the very bottom of your application, you will force yourself to start thinking asynchronously. So executing a function, and that's it, and then executing the query to fetch the state of the system. So CQRS as approach, if you want to put it almost a philosophy of programming, will naturally guide you through asynchronous operations. Of course, if you're using infamous microservices, this is also where CQRS is working well. And whenever you have disparity between reads and writes, and most of applications we're building today are not CRUD systems. Most of the applications you're building today will have some kind of disparity between reads and writes. You will be able to achieve separate optimizations for the reads and writes and actually solve your problem with reads without affecting your writes or the other way around. And yes, you can use CQRS without event sourcing. You can, because you're pragmatic. So you can introduce CQRS without introducing event sourcing. You can use either SQL or NoSQL, be pragmatic, use whatever works for you. And sometimes, for example, you don't have to create aggregates. You can create projections right away, so you can skip some steps if you don't need them. Of course, there's no silver bullet. You remember Fred Brooks. So when you want to use this, when you have complex application, complex domain, if you're building simple CRUD application, you don't need have it literally. You don't need patterns, you know. You're building simple applications. So whenever you enter technical marriage with something like this, have clear answers. Why would you want to use it? So today, we actually learned why developers love change, because this is what keeps us employed. Because if you imagine a world without changes in software requirements, we would build applications, that would be it. So actually, everything we are preparing for is making changes to the applications. And when you look at the concepts we are using today, most of them were invented in 60s, 70s, 80s. So when you run into sentences like CQRS or CQS or your queries, querying database should not, stating questions should not change the answer, go beyond it. Go find the source, read it. And when you understand the principles, then it will be easier for you to comprehend current technology. So for example, if you run into React, if you're familiar with Elm, with model of Elm, you will have easier time understanding something like React or something that comes after the React. Or if you learn functional reactive programming, you will have easier time finding your way in new patterns, new technologies that are emerging. Don't be a Sith, don't deal in absolute. Don't use words like always, never. Be pragmatic, turn off your autopilot. Think about every single project you're building and make conscious decision and be prepared to defend them in front of yourself and of course to your team. And when we start doing like that, life will be simpler because we will have arguments and every single project is different. So why should all these different projects have different, same implementation? The way you implement the systems should be different because you have different needs, you're solving different problems. So how many databases you need? Infamous answer, it depends, because it really depends. But we should continue this sentence. It depends on the actual scenario. It depends on your needs. It depends on the problem that you're attempting to solve. There's no silver bullet. Be pragmatic, consider every single project and make decisions based on that. Thank you. Any questions? Usually when I build a product, when I deliver it, if I don't hear from customer, from client for like 6 months, I know that either they are not using it or they are not using it. All right, thank you.